Right. Hello. There we go. We're all sorted. So we are going into week 4 of Advanced Labs, and we're going to be covering game trees and Minimax, and then how to optimize them. So to explain game trees, what we're going to use is we are going to be playing a game. In this game, we have 2 players that are in kind of going against each other, plucking petals off of a flower. Right, so you each take it in turns. You will either remove 1, 2, or 3 petals from the flower from your go, and whoever plucks the last flower off loses. Whoever plucks the last petal off the flower loses. So we'll just kind of play and say that we take a go, and the number of petals on the flower starts with 6. I'll take the first go. I'll remove 1, which will bring us down to 5. Then we'll just basically say that they take their go. We'll say that in this case they'll take, well, it doesn't really matter whatever take they get, but we'll say they take 2 off. That'll bring us down to 3. I'll then take 2 off, brings the other player down to 1, and then they will lose. Now, say we do a different one where it starts with 13 petals, and then the other player goes first. We'll say that they just take 1 off this time, which is bringing it down to 12. I'll take off 3, bringing us down to 9. Then they will take off, we'll just say they take off 2 this time, which brings us down to 7. I'll also take off 2, brings us down to 5. And then again, say they take off 3, it'll bring us down to 2. I'll take off 1, brings us down to 1, and then I win again. So what I've shown you here is the power of game trees by always being able to win, as I got to decide what number of petals to start. The way that I played this is it didn't really matter what the other player kind of got. I was making sure that we were always at a certain amount of petals. Like, if it doesn't matter which kind of petals the other player would choose, I'd always be looking to first get us to 9 petals, then to 5 petals, and then lastly to 1 petal. And then with the previous example as well, I was doing the same. But now using game trees, we'll be able to know whether a game is winnable if both players play optimally. You'll hear about a lot of kind of logic problems or kind of massey problems, and they'll always make the argument of, is it possible to win, or like, how will you be able to win if the other player's playing optimally? It's kind of, you're looking for kind of the best route to succeed that you will win. And this is where game trees come in. So game trees are a method of representing decisions being made in a game on a tree. For the game above here, what we're going to use is we're going to do a tree when the petals are 5. So we're going to draw a tree where we have all the possibilities. I'm going to use squares for when it's my go, and I'm going to use circles for when it's the other person's go. So I'm just going to go and fill this one out. So we're going to start with 5. Then there are 3 possible outcomes from this one. They take 1, they take 2, they take 3. Then obviously for this one, I can just get them down to 1 by taking off one petal, that's fine. For this one, there are two possible routes. I take off 2, which will get us down to 1. Take off 1 will get us down to 2. And that'll be 3, 2, 1 again. Just bear with me whilst I draw all these out. And then this one's going to be 1, this one's going to be 2. Sorry, just bear with me. I'm drawing shapes wrong. And then lastly is this one here. So this is what our completed game tree looks like when we filled it out, with these levels being my turn, and then these levels being the other turn. We know that any case where it's a square and it's a 1, I win, but if it's a circle and it's a 1, the other player will win. So we'll be looking at this game from the perspective of player 1. So we'll be seeing if player 1 can win. For each node in the graph, we want to calculate its expected value, which we're going to represent with EX, and we'll go into what EX represents in a second. EX is going to show the likelihood of each player winning at that state in the game, depending on which route they take. Where one player is player 1, so if there's a 1 value, it means player 1's going to win. If it's a -1 value, it means player 2 will win. X represents here the game state, in which, in this case, the entire game state can be represented by the number of petals left and whose turn it is. So X is the game state, so it'll be 5, 3, 2, and so on and so forth. But EX will be a value which determines kind of the expected probability that we'll win, negative being in favor of player 2. So we'll start at the leaf nodes and work our way up, and we'll kind of note down on here all cases that we win and all cases that the other player wins. So this is gonna already slightly swift from what it is, but that's fine. So as I said, we'll win on squares with 1, so they're gonna all have a value of 1 in them. I'll just check if this shows up quite well in a second. Just say if it's a bit hard to see. Give me a second. I'll just go over and rewrite these so they're slightly bigger. For the squares with 1, and then for the circles we're going to use -1, which I'm just going to, for the sake of these, I'm just going to put them below because it's going to be easier to see them that way. But yeah, we'll work our way up the tree. Sam, it's fine. They'll just be flipped values. I'm saying that we took the first go here. For squares, we're playing. Now we'll work our way up the tree. We assume here that both players will play optimally. So if the current node is a square, us, we will always choose the maximum from the children, right? Maximum of the child nodes. This is the opposite for a circle, who will always choose the minimum of the child nodes. If there is only one child node, then the parent node will just takes on the children's EX. So starting on the far left will go up. So circles, if they're given a choice, will choose the minimum value, and squares, if given the choice, will choose the maximum value. So this one's going to have to just choose a 1. But then for this one, we got the choice between 1 and -1, and because we're a square, we're going to choose 1. However, for this one, we've only got the choice of -1, so we're going for that value. Again, it goes up 3 choices. Most likely, one we're going to go for is a 1 here. Oh wait, sorry, it's a circle, so it's going to be a -1, sorry. Then for this one, we've only got one choice, -1, so that means that one's going to choose -1. And then this one over here is going to choose 1. And then last step is obviously for the root node. We're a square. We've got a value of 1 that we can use. So this means that if we play optimally, we can guarantee that we'll win. There is a possible route where we can guarantee that we're going to win. Going through all the nodes. How is that wrong, Sam? We can win from 5. Look, we remove 3 petals, leave it on 2. We would lose on 5. That is a good point. Yeah, okay. If both players play optimally. Interesting. Oh, I see what I've done now. Yeah, okay. Yeah, these base values should be inverted just because if it's our turn on a square with a 1, then we'll lose. So I'm just going to flip these around and then correct it. That's going to be that, that's going to be that. The rest of it's still fine. So what we can see is that from a state of 5, it's not possible for us to win. It was rigged against us from the start if our players play optimally because the other player can always make it so that we're going to lose on their turn, no matter what we choose. Yep. Thanks, Sam, for correcting me on that one. But that's how we can, like, for like a small scale game tree, that's how we can kind of guarantee that we're going to win. This procedure is kind of called Minimax. Player 1 is trying to maximize the chance of them winning, while player 2 is trying to minimize it. This procedure is very useful in determining what move to make next, but let's say for the game above we have about 100 petals. It's going to be a very large tree and takes a very long time to compute. Other kind of examples is up until recent kind of developments in like AI and that, computers that would try and win chess games would use game trees, and they'd go to a certain depth, but they can be limited by their computer like hardware and processing, because the game trees would get very large very quickly. So they had to kind of modify it so that it was still possible and it wouldn't take them like several minutes. It takes them several minutes to kind of calculate the next move. We're going to make our algorithm more optimized by using 2 key optimizations. From now on, I'm going to be talking about an arbitrary game rather than the petal game. So it's just going to be a generic explanation for it, right? So our first optimization that we're going to be doing is, if we are limited by how like deep in the tree we can go, we can't calculate necessarily a accurate expected value, so we're just going to estimate it instead. So we'll keep going with the chess example, but you can only look at a few moves in the future before the tree gets too complex for most computers. And you cannot give anywhere near to simulating a full game, as we said. This means that you can't get an expected value of 1 or -1 until like you're within a few steps of like a checkmate, basically. As you cannot, but from the start, definitely not going to be possible. So you cannot be certain who will win without simulating the possibilities. Instead, you estimate your value of EX using a function that takes in the state of the game and gives out a value. For a game like chess, you can use a function that basically applies certain weightings to different pieces. So say a pawn is worth 10, has like a weighting of 10, whereas a queen is a weighting of 100, because obviously it's a more important piece. You add up, like, if you keep going with something, you then add up all the white pieces and subtract all the black pieces, then do the algorithm we've seen before, with player 1 picking the max of children, player 2 picking the minimum of the children. But what you'd get is, if you wanted to keep it within 1 - 1 bound, you then kind of have it work in decimals, and what you'd get in your game tree is, instead of storing game state, you'd be storing the expected value. So you'd kind of go from the leaf nodes of your level and then keep going up, and you'd have your function to define weightings of different pieces. If we're using a chess example, or based on the context of the game, you'd have certain weightings that would allow it to not have to get too complex, and you're estimating your value relatively well. Obviously, the more accurately the estimation, the better it's going to run, but that's kind of the trade-offs that you're going to be working with. And then you just do as we did before. For your turn, you'd be choosing the maximum value, and for the other person's turn, they'd be choosing the minimum value, going for the minimax. Now, the other optimization that we'll be doing is something called alpha-beta pruning. And what alpha-beta pruning does is, you know that given like a set of all possible kind of moves that you can do, you will be able to kind of look at certain moves and be like, there's no point going down that route, that's going to show that I'm going to lose. Especially like if you're playing chess and you put a piece somewhere where the other player can take it and you won't get anything benefit from that, it's just not worth doing. So you don't then need to do all the calculations down that route. So how would you go about doing this with programming? So we're going to just show a snippet of code, a snippet of pseudocode to explain kind of how this is going to work. And what this will do is, this is a kind of a pseudocode idea for how alpha-beta pruning is going to work. You will start by having 5 values be taken in: the node that you're currently at, the depth that you're currently at, what player you're currently on, and then 2 values, alpha and beta. We'll go into what these represent in shortly. Yeah. So you're going to mainly be starting with, you're going through each loop and you're going to be saying, right, you're at your maximum depth that you're searching at, or if the game is won, then you're just going to return your estimate of that game state. However, if it's like your turn, you're then going to be looking to kind of compare your different routes and kind of see if it's worth going down certain routes. And again, for the other player's turn, I'll show this code back up in a sec. I'm just going to go through the board with some diagrams to kind of explain how this is going to run. So we'll carry this algorithm out on an arbitrary game to demonstrate how it works. For this example, we'll have a max depth of 3, and we'll have it be fully balanced before we go through it. As a quick note, what we're going to be representing in the center of the nodes, it will no longer represent the game state, but rather the estimated value of that node, so the EX. So I'm just going to go and draw about this. I'm going to need to draw these circles bigger. And then just draw some connections. Bear with me a second. So, what we'll do first is that we need to, from the root node, we need to kind of stem down the left and then keep going all that. So we'll go here, then to this node, and then we'll go down this kind of path, and then we'll then go and do the right half as well. Yeah, so there'll be states in the middle, which will represent our expected value, but there'll be 2 other numbers floating around. And at the top, it's going to be alpha, and at the bottom, it's going to be beta. To start with, we are going to assign, so I'm just going to show it for the first one. First alpha value is going to be -1, and our beta value is going to be 1. It'll kind of, okay. Yeah, so we'll kind of go down the route and we'll go down there. So firstly, what we need to do is we go down the left tree and copy our, as long as it's not a leaf node, we'll copy our alpha and beta values across. So we're going to have -1, 1, -1, 1. Now we're now at a leaf node. We'll say that for this leaf node, we don't need to care about alpha and beta because the alpha and beta values are to do with comparing the different possible routes you can take from a node. And since a leaf node will have no children, then it's not worth kind of it out. So what you do is you'll look at the leaf node, and the leaf node will have a value of EX that will have been calculated by your function, your estimating of that value. So we are just going to use some arbitrary values for now for the sake of this example. So the first leaf node we'll say is a value of negative 0.1. And since from this one we are looking for kind of to increase alpha, when it's our turn we're looking to increase alpha, when it's the other turn we're looking to decrease beta. So our alpha value is going to then change from -1 to -0.1. And then we look at our other leaf node, which for what we're going to use here is going to be 0.3. And then once again, because that increases alpha, we are then going to change our alpha in this top node. And then because we've done the notes, that means that the value of this node here is going to be 0.3. Then as we go up, we're saying when it's the other player's turn, we're looking to decrease beta. 0.3 is less than 1, obviously, so that's going to then change to 0.3. Then what we need to do is look at the other child. Now the other child doesn't have any alpha beta values across. Every time that we have to access a new one that doesn't yet have alpha beta values, we just copy them across from its parent node. So this is going to be -1, this is going to be 0.3. We then are going to look at our leaf nodes. We're going to say for this case that it's 0.5, which is going to reset our alpha value for the parent node to 0.5. Now, something's going to happen here, which means that we don't need to look at this one, and that's just because alpha is greater than beta, showing that player 2 would not pick this route, just based off of the nodes that we have searched. When alpha is bigger than beta, it means that it's a route that player will, like any other routes the player will not take. So we don't need to calculate from this one. So this one's going to be null, and then this value here is going to just become 0.5, if I'm correct, Sam? I hope I'm correct. And then we compare up 0.5 is not less than 0.3. Yeah, greater than or equal to 0.5. So because 0.3 is less than 0.5 on this one, then 0.3 is going to be the overpowering value. Now we've completed this kind of half of the tree. We then have one of our values here. Obviously for us, 0.3 is going to be greater than -1, so we are then going to change our alpha value in our root node, and then we're going to carry on to the right side. So we take for the child, we give it the alpha beta values of its parent, so this is going to be 0.3 and 1, and that's going to carry down here, so 0.3 and 1, and then we're looking at children nodes again. We're going to go through this one, so we're going to say it's -0.6 and -0.4. Now, -0.6 is going to have, here it's going to have no change on our alpha value, because alpha is already bigger than that, and again for -0.4, that's going to change our value here. Again, doesn't change our alpha beta values. Now, as it's our turn, we are once again looking to take the larger of its children's. So we are then going to set its value here to -0.4, which is going to set this one here. And then as this goes up, this is going to change our beta value to -0.4. Because as we said, for other player, they're looking to minimize beta and take the smallest value to be their EX, and for our turn, we're looking to maximize alpha and take the largest value. Now, once again, what we've achieved here is alpha being greater than beta, which means that we don't need to look at this section of the tree, and this is going to set our value. It'll set our value to -0.4 when it's done. Yep. Cool. Yeah, so then this will set the value for this node to -0.4. And then obviously this would span up, -0.4 is not bigger than 0.3, so it doesn't change our alpha value. But we're now at the root node, so we are just looking at our current ones. It's our turn, we're going to take the bigger value, it's 0.3. And then what we get here is that its value is 0.3. Now, what this means is that, correct me if I'm wrong here, but what this means contextually is that if from the root node, on our turn, we have a 30% chance of winning, and we want to keep following that one, so it'll go 30% chance down to here. Then for their turn, because they're wanting to minimize our chance of winning, they're going to choose that route, and then we are going to go down, we're going to choose the most probable route of us winning, is how it's going to run. Not really 30% chance. Cool. Is it just that we are our optimal route? Okay, so it's an indicator of which is are we going to win? And because it's positive, it means that it's an indicator that we are possibly going to win. We are going to want to keep going down the routes that on our turns that maximize. So obviously we'll go down this route here, but obviously because this could be a very complex game, it could be like 16, 20 levels deep. We don't know what the value is. Not exactly like percentages is what Sam's saying. So it's indicating that we can win. And so we'll just with our estimated EX values, and so we'll go down maximizing our outputs, and the other player will try and minimize our victories on those ones. And that is game trees, Minimax algorithm, and how to optimize them. There isn't other content to go through. If there's any questions, then we can try and answer them. If people are currently watching who have questions. I'll also stick the code back up for the pseudocode backup. Sam says there was a small error, just a slight typo, in the else section where it should be the worst value should be set to the minimum rather than the max value. But if there's no other questions, then that will be all. There isn't any problems to go through this week because we couldn't find, we couldn't find any that would be not too complex to do. So that's just how the game trees Minimax algorithm works with main methods of how to optimize it for larger trees. I think that's everything. So we'll call it there, and we'll see you in 2 weeks for the next one. Because we'll be out of lockdown, hopefully. It should go back to Sam doing the content, and then I'll go through some stuff afterwards with some coding challenges. Okay, thank you all for coming, and we'll see you all next time.